All good? Thank you so much. First, let me thank you because this slot is a tricky one, right? You have a lunch at the other side and then you have missed that and then you're joining this session. Highly appreciate it. How are you doing? Possible? The slide? Thank you. In the parallels of data scientist, I might be an outlier here today. We are at an biggest AI conference, and then people are all talking about big data, and here is a person who is standing in front of you and saying, how can you build a model with a small data? Maybe you will empathize with me after we go through this session that why we are speaking about a small data here. Okay, before we go there, if this is the number being displayed, is there an unit or a fact that you can associate to this number? Any random guess? Being available for the healthcare realms in a given year, which is roughly 2,314 hexabyte of data. It roughly translates to 1 exabyte is 1 billion gigabyte. And just for putting a context, if you feed all this data together into a current capacity of hard disk, it can encircle almost 3x of the Earth's circumference. Now, the problem statement is very clear, right? It is not about the challenge of data. We have enough high quality AI models. With that being said, healthcare accounts for almost 30% of the world's total data that is produced. And it is growing at a CAGR of almost 36%, which is almost 10% more than a manufacturing, rather financial service, and 6% more than the manufacturing. So the amount of flow of data in healthcare is immense. And with that being said, that was from the perspective of data. Now, bit shifting the focus to AI, this graph, most of you might recognize, which is an ImageNet challenge graph, right? And every year this competition gets held of ImageNet where a lot of data scientists and the teams apply to this. And this is a computer vision challenge where millions of images are annotated from cat to dog to umbrella and so on with an high quality annotations. And every person or the team tries to get the best of the model on this data. And you might also recognize that the current deep learning kind of things where it kicked off was also because of this event that happened in roughly around 2013 timeframe. There was the AlexNet that came into picture, which is a convolutional neural network, which was having that right ability to uplift than the previous year almost by 10 to 12% the accuracy levels of top one accuracy. Now, earlier to that, all the computation was within a percent or a 0.5% or so what would be the change in top one accuracy. But here comes, after 2013, deep learning models and then sudden uplift of close to 12 to 13% in accuracy levels. And it indeed continued across the years. And every model post that is one of the other flavor of a deep learning, right? Starting from ResNet to Inception and so on. If that is the case, you might attribute this to two fields. You said, you can say that GPU came in, the new architecture of deep learning models and so on, right? Very fair to give the credit to them. But one other thing is, it's also the ability to have this rich quality of highly annotated data because of which these kind of models were potentially evolved and ability to reach to the stage where it was able to beat this classification accuracy of the classical machine learning models or so. With that being said, I'll throw upon this question. Do we have this luxury in healthcare with respect to data? Yeah. And to put into perspective, in today's world, we use only the tiny fraction of the data that we saw of 2356 exabyte. Only tiny amount of data is even used for building our AI models. For us, if this could happen, if it's possible, to use vast amount of data that we collect and use it for building the AI models, what would be the impact? Was the question that we put across. It might sound easier. However, if you look at first challenge itself, we said about ImageNet because of apple-to-apple comparison, because ImageNet is a kind of computer vision, all the images being put across. Let's draw the parallel analogy to the healthcare world. Some of the sample publicly available large data set of medical imaging are following. They are by deep lesion by NIH for a CT modality, and there are 32,000 images, right? All these numbers are in thousands or hundreds. Chest X-ray or intracranial hemorrhage detection, the CT images, close to 25,000 examples, or the TCIA collection, or Alzheimer's disease kind of subjects evaluation, which are 2,000 plus subjects. And the first challenge itself is the ability for the people to even embrace these kind of data, to even build a model itself is small. So the challenge of we saying a minuscule amount of data being used to build still exists for us. So let's address this challenge one during our technical solution aspect. How did we solve this? So one fundamental problem is ability of high quality annotated data set that could be used for building AI models in healthcare. Now, let's look at a second challenge that we have. For most of the AI model building, this flowchart would hold good, right? Irrespective of the domain, I would say. It begins with a hypothesis, what you want to solve. Then you define clearly a problem statement for that. Then we deviate a bit here in healthcare. We go on to identify a clinical site, which roughly takes almost 2 months of time. Then you go into this process of signing the research agreement, ethical approval, and so on, then collection of data, finally towards building the model and validating the model. And this timeline might vary based on the use case and the kind of collaboration you have, but this is an average of almost 20 studies within the Philips environment that you would say, give or take, this would be a rough timeline that you can see. An interesting part is the box in the red, right? Most of the time, it goes in getting this data right and then also getting the approvals such that we can go ahead with building the model. When we deep dived into this, why is it that it takes so much of time, right? Why is it not easier like the other verticals? And I don't deny that other verticals don't have a challenge, but at least with the healthcare, what are the problems? All the problems, or at least the challenges, you can attribute to one of these 5. It could be administrative in nature. The hospitals don't want to share it because they don't have any resources, or a diagnostic center don't want to do it because they don't have the resources to even spare for this use case because that is not their priority. Second could be political in nature. I don't want to do it. What is in it for me to share the data? The third one is ethical in nature. The entire data belongs to patient. We don't have any right to consume it, in spite of all the consent being taken and so on. Other is technical. There is no clear know-how of ingestion of data from the source to the destination such that people can build, or right data pipelines not being established and so on. And third, obvious, the last one could be the commercial also, like what is the amount of value that you associated with a patient data, right? That could be the other reason. Now, if these are the barriers for sharing the data, the question that we have is, how can we reduce this entire time for development of an AI model in a healthcare, which could effectively gain efficiency for developing this model? So 2 hypotheses that we said, how can we solve the challenge of the less data that we have? And the second one is, how can we solve the challenge of sharing of the data when the data is available? With that being put across as a problem statement, the approach that we have is less is more. And how do we define is, if we have a very small amount of data, let's use that effectively and extract more information from that. That's what we mean by less is more. And we'll try to see an example of that. The other is, if sharing is a problem, don't share the data, but if you can bring the research directly to the data itself. Yeah, that's the other way of thinking, which could potentially lead us to faster, better, and a cost-effective way of developing the AI solutions in healthcare. Now, coming to bit on the technical solution, those are all good, but how do you solve this problem? An approach for us is a combination of hybrid AI with active learning and a federated learning to build these models. And this would be what we will try to look with an example in each of these cases, how we are able to address this challenge and build a high quality AI model by combining these three technical approaches. So the first part of the solutioning would be to overcome the challenge of data paucity that we have using a hybrid AI. And we go into what does it mean. In a traditional AI-driven approach, it's all about collecting the data, applying it to one of the best models that are available, and then it has an ability to spit out whatever the class it is if it is a classification problem, right? But even though the data is heterogeneous in nature, still we'll have a challenge with this approach if the intermediary steps are not taken care. And what do we mean by hybrid AI is following. Before you even apply the data to the AI model training, you might have said EDAs and so on obviously gets done. What is so different? We call it as a pre-processing step, and this pre-processing step might be a bit different than a traditional way. The pre-processing step could be about the noise removal within the images, the kind of motion artifacts when the person enters into CT or an MR. It is not that the person is always stable. There is so much of artifact of the movement of a subject that happens. How can you compensate for these motions that gets replicated in the images? How can you eliminate the artifacts within the images? And having that strong pre-processing even before you feed the data to the AI model is one of the steps. The second one is on the anatomical intelligence. As a human body, between a sample A and a sample B, almost 95% of them we are same, right? The lungs are at the same location, the brain is at the same location, esophagus is at the same, the liver is at the same location. Exploiting this anatomical intelligence and adding that to the model is significant, right? When you have a very small data available. And how do you do that? Would be one of the examples that we'll show, but before even you apply the data to the model training, augmenting that with the right anatomical intelligence is a key for us. The third is on the clinical knowledge. Third is on the clinical knowledge. The reason being, the medical professionals, they learn almost at 10 years or so in the curriculum, right? And they go through a vast amount of books and they assimilate this knowledge. And if you have a bit of an interaction with any of these practitioners, you would come to know that the reasoning when they come with a diagnosis is on the following way. They have assimilated all the knowledge across their academia, and then whenever a patient comes in, they ask a set of questions to them, right? Did you had this, what time it was, and so on. That is called case history, right? And what is happening in the background is they are trying to create a small flow chart within their mind. If this is there, then this is the symptoms, and this might be a diagnosis or a prognosis that I want to put across. How can you put this clinical knowledge within the model is the question that we have in the hybrid AI. Because this is quite extensive, and most of the decision making, as they call it as an evidence-based medicine, happens with a fixed set of rules. And how can you embed that? And obviously, the last one is not new to only to this domain, but it is a synthetic data generation, augmenting it in the right way such that we kind of combine together and then put across the final data to the AI model training. Now, this seems interesting, but now let's take an example to say, what's the difference between a hybrid AI and a normal AI, and is there a significant improvement in the outcome that we want to do? And for that, we use this use case of stroke hemorrhage detection. Just to set a bit of a context on the background of it, a stroke is a phenomena which happens with reduced supply of blood in the brain region. It could potentially because of rupture of an artery or because of a blockage of a blood vessel, right? And if that happens, it could be potentially a paralysis or fatal. And it is so important at an emergency setting environment that as soon as a person comes with the symptoms of a stroke, they need to kind of differentiate between whether the stroke is because of a blockage of an artery, which is called as ischemic, or is it because of rupture of an artery, right, which is called hemorrhage. And The caveat is also important here because if the treatment goes other way around, right? The other one way, if it is a blockage, you need to provide a medicine which can remove that block, which is called anticoagulant and so on. Now, if the treatment is reversed, it also is a fatal for the person, right? So it becomes so important that they need to be having a precise diagnosis, what exactly is the stroke type. Is it ischemic or is it hemorrhagic, such that they can plan their treatment well. And as they call in the stroke treatment, time is brain. More the time you delay, the impact is quite high on the person. With all due respect to cat and dog classification, this is something very different, right? Here you make a classification, it is really impacting the life of a person at the end of the day, right? Now, with that being said, this is kind of a holy grail for a data scientist when they see this kind of an image. Say a CT image is there, and there's a white patch on the top right corner. And when a hemorrhagic stroke happens, you see on an image the white patch. And best of the people would say, yeah, that's a cool problem because I can really identify the gradient of this pixel, change the variation, I can put across smart algorithm, and then, hey, draw it and then say this is a hemorrhage, right? So that would be the initial thought. But let's look into a bit on why it is not really the case. Bit busy slide, but this is what encompasses the hybrid way of looking at. Whenever you have the first CT scan being taken for the patient who had potentially a stroke, on the top, this is what you would see on the reader's screen on the radiologist console. Once you have this, the same intuition that you had earlier, saying white patch wherever it is, I will try to mark it and then say that I classify it as a stroke, kind of goes away because you might see here as well that it is kind of a white patch also in the circumference, which is nothing but a skull structure of a thing. So if the model just learned that there is a white patch, then obviously it will not work well. Then you go on to the next step, what we call it an anatomical intelligence. We know how the structure of the skull is. You apply an atlas-based modeling on top of this and then only try to extract the region of the brain that you need, which would potentially look like this, and the registration and so on are also part of an ML-based approach, but it is about exploiting the anatomical intelligence, what already exists. Then you try to take this and go to the next step, which is you want to bit curate this entire image that is come in, and then there are a lot of kind of boundaries which are not connected and so on. You do a line filling algorithm like Bezelman lines filling and then try to come up with a nice concrete structure on top of it. Post that, you can also identify which is the inner boundary and the outer boundary of the region within the brain and external to the brain. And then you kind of do a bit of a brain region extraction. You might also see that when a scan is taken, on a CT, it directly goes in this fashion. You also get these eye sockets. Those are the eye sockets. So, but those are of not interest to the radiologist who want to do this diagnosis. So you remove out all those parts and only take across the region that is of most interest to us. So this is embedding of the clinical knowledge within that. And then other interesting thing happened during the process that white patch is good, but when an X-ray hits the CT or the brain, you have all the skull structure, there is a kind of reflection that happens on the outer boundary, which is called scatter. And this scatter of X-ray also represents in a way of a white patch. So it becomes quite important that you need to eliminate these kind of artifacts that come during the acquisition and then correct it such that you don't get a false positive when you train your model saying white patch is always an hemorrhage. And finally, you extract this entire brain CT image. Then you also say, when should I stop taking all the slices, which is, when a whole body CT is taken or a head CT, you need to at least restrict which is of not of interest to you. And then we restrict using some of the stopping criteria. And finally, take a projection, which is called maximum intensity projection. You take it via different axes of views, and then you have the final model that comes in on top of it. And this is the model, finally, goes as a trained deep learning model, and we provide at least the 3 different classes, which is it could be hemorrhage or it could be non-hemorrhage. But the interesting part is the in-between one. If you are not confident enough, don't make that prediction, right? And identifying that right cue to say, I'm very sure of this measurement that is going to come out and this classification label. If you are not, Then we bucketize into that yellow traffic light for this. So this is fundamental difference between an AI approach, where in an AI approach we said, you have a lot of CT scans, find out the best of the model that is currently available, just apply. In case of hybrid AI, we say, hey, augment that with all the anatomical intelligence, clinical knowledge, and the pre-processing in the right way, such that the model has less work to do. If that was a thing, do we really have a performance benchmark comparison? Do you really say that hybrid AI really works compared to a normal? In order to just do this, so the experimental setup was following. You have 379 CT subjects, which are on a trained set, and 79 test subjects, which were completely unseen by the model, the golden test set. And a model was modified inception ResNet v2, which was kind of intermediate between the best of the class models and not the classical machine learning model. And if you take a normal AI approach with bit of a pre-processing, I would say, and then apply, these are the kind of results that you're going to get on your test set, right? Hovering around 0.6 or 0.5 or so on your test data. But once you apply the hybrid AI with all the pre-processing steps that we saw, you're almost hitting at 0.95 on this data set that was proposed. So one of the things that we want to call out here is the paucity of data is indeed there. However, extracting that information from the less data, which is less is more for us, that's what we started with, we could potentially reach to a stage which could be of the level that any radiologist would need it, because 80% is not good enough, because you need to always have that ambiguous nature. Should I rely on this algorithm or not? Yeah. With that being said, that was the first part of the story. The second part of the story is about having high quality annotated data. And we all know, and I also see one of the physicians in the room as well, the amount of time that they need to spend to annotate, and also the amount of money is spent on doing it is quite high, which is really a challenge. You can't have a same skill force who can annotate a cat or a dog within half an hour of training versus having a radiologist in your room whom you give these images and then get them, right? So how do we overcome this challenge of having to overly dependent on the skill annotation, right? We do need it, but at least we kind of overcome with this technical solution of active learning. Most of you might have applied this concept in machine learning called active learning, which is about you create an initial seed label or a seed model, the same way that what we had in a hybrid AI, the initial model that comes as an outcome could be the initial seed model. Then this model, we try to take all the unlabeled pool of data. In this case, for example, we have thousands of CT images. We don't know whether it's a hemorrhage or a non-hemorrhage. Take those data and pass it to this model. And this model would obviously spit out the classification labels, whether it is confident, non-confident for the use case that we have put it. Based on the query mechanism, it could be a pooling, it could be a selection. You try to identify those cases which are highly ambiguous. And the way you can do it is the model which is not confident on a use case is equivalent to a model which is highly ambiguous, right? And the rationale behind is, if you keep showing the same kind of data to the model, there is nothing new it can learn. The hypothesis here is try to get those data points which really add some more learning to this model. And that is called query picks. And it could be multiple algorithms that you can apply on this. And finally, only give those images which are ambiguous in nature to the oracle. In this case, we call it a skilled physician. And they further annotate this, and it goes into the sample back. And this loop continues till you are comfortable with the kind of class imbalance that still exists, and then you proceed further. Now, with that as an approach that we put across, now let's look at bit on comparison between this concept of active learning versus that of a normal learning that we put across. So the data distribution still remains the same. Like the last experiment, we took 379 subjects, we built an initial hybrid AI model. Now, we had access to close to 6,000 subjects data. Out of that, it was divided into 5,000 for a training and the 1,000 for testing. And in case of a normal learning approach, which is nothing but a classical way of doing, you take the initial seed model, this was the accuracy on the test data that you got. Now transfer learn it on all the 5,000 samples, because you do have labels for all the 5,000 samples, and then test it on this 1,000 subjects. That's the kind of accuracy, sensitivity, and specificity that you are looking at, right? The use case here is you already have taken the entire subject data to train it. But the active learning approach is a bit different. We say, don't take the entire 5,000 samples, kind of look at these 5,000 samples and feed it to the base model, and then try to find which are ambiguous in nature. And what you see in the second row here is that close to 555 samples are ambiguous. Now, how do you define the ambiguous? It could be based on a confidence interval, the change in the entropy, and so on. Say any image that is in the confidence range of 0.4 to 0.8 is ambiguous zone for us. And if those are the case, only send this 555 samples back to the skilled physician or an oracle who can do the job of doing the annotation. Then pass it, the new labeled 555 sample, back to the same cycle and keep continuing this approach till you reach a substantial number where it is not more significant anymore. With that being put across, what you see finally is the ambiguous cases keep decreasing across the active learning iterations. And finally, with almost 1,000 samples, right, which is 1,000 by 20, almost only 20% of the data, we are able to get the same model accuracy performance benchmark versus getting all the 5,000 labeled. So the 5,000 labeled was somewhere around 0.86 of accuracy level, coming to the active learning model of the 12th iteration also comes to almost the same one. So what we want to drive the message here is, it's important that what kind of data gets annotated. And in order to do that, you can use this technical solution to employ it. And we have seen a reduction of almost 80% in the data annotation effort with this. With that being said, let's look at the second problem challenge that we said, which is about sharing of the data. We said people don't share the data, and how can we do or overcome this one? Federated learning as a concept is not new. It has been used across different industry, but how do we operate is in the following. You have this initial model, which is hybrid AI plus the active learning based approach. Then the model that gets built here is shipped to every hospital that is there, right? So the model runs locally on the hospital environment without pulling the data from the hospital to a central repository. And each of these models have a local learning of the data that is being put across. And finally, the weights of the model are combined together to build a global model, which is the aggregation of this model, right? And finally, this global model is the one that gets shared. And it doesn't stop here, and there is a repeat process as well. And this model also comes back, finally, the global model also is shipped back to the local nodes, or in this case, the hospitals, and they relearn, and this process keeps continuing till you have a convergence associated. So what we solve with this problem is twofold. One is we don't need to build or get all the data centrally and then do it. And the second one, obviously, is the barrier of sharing the data. And to put into context of how the federated learning is done, let's, for example, take a data set which has an event and a non-event. For simplicity, we just take a two-feature set. And assuming you want to build a classifier for this, the best decision plane would be something like the one on the green line, right? So where you want to differentiate between an event and a non-event between a patient. If the data is not centralized located, it is at a different hospital site, you build these local models of 1, 2, 3, 4, and the decision plane for that particular local data would look something like what you see, the hashed line or the dotted line. Yeah. Now, once this model is getting built in this hospital, we can transfer this back to the global data set, which is nothing but you take the weights of it and then put it across and kind of average them and then send it back to each of the hospitals. So you do have now the average solution there. And this is at the first iteration, right? And this iteration keeps going on, and the decision plane keeps varying. After some time, the interesting one to note is on the top one, where the centralized learning solution, what was attained, we will be able to come closer to that with a distributed way of learning. Almost the decision boundary that you finally get would also be the same. Yep, this is almost at a 50 iteration, and then after 100 iteration, and then close to 500 iterations or so on, you can see there is a kind of overlap between the distributed learned model versus that of a centralized learning solution, meaning that even if the data sources are dispersed, they are at a different systems, you have an ability to combine and then build a global model out of it. Now, to test the accuracy levels, indeed, this is a good, but indeed works in a real time on the same data set that we put across. So kind of took the two hospital networks here, number of epochs, and we run on two different nodes. And you can see that on the accuracy of the first hospital, it was 0.86 or so, and the other node, which is at 0.89. And when you merge both of these models with a common data source and then build a model, you hit somewhere around 0.9 of accuracy. Now, if you don't combine them and do the same approach that we just described a few slides, then you almost hit the same kind of accuracy levels. So merging the data is not really needed if you have that as a constraint at your end. With that being said, I kind of come to the last slide of it. In conclusion, what we say, we began with less is more, and that could be achieved by a combination of hybrid AI, active learning, federated learning combined together so that we can build quality AI models, which should help us build at a faster rate, which could be easily shipped. And it could be cost effective, both in terms of the amount of annotation effort that is needed, and then also the barrier to access. And it could be better because it is a bit generalized. You no need to worry about only the ethnicity of a particular geography. If this federated is across the geography, you can take that pool of data, combine together, and then still build it, which is a highly generalized model rather than a locally distributed model that would typically come if you are only adhering to few healthcare providers and then saying there is a still bit of a bias in the model coming in. With that, I end, and I also like this final quote where AI algorithms can't be expected to perform at a higher level than their training data, but it should deliver the same performance when they are used with the same schema of training data that comes for their inferencing time. With that, I pause it here and open for any questions that you have.